Welcome back. Before we start our deep dive into today's topic, please take a second to hit that like button, subscribe to the channel, and turn on notifications so you never miss a technical breakdown. It really helps the channel grow. Welcome to this comprehensive tutorial on Apache Fluo YARN. Apache Fluo is an open-source framework designed for incremental processing of large datasets. When combined with YARN, it becomes a powerful tool for scalable, real-time analytics. In this video, we'll explore how Fluo leverages YARN resource management capabilities to enable efficient distributed computation. Whether you're new to big data or looking to expand your toolkit, this tutorial will guide you through the core concepts step by step. Apache Fluo is an open-source framework that specializes in incremental processing of large datasets. Unlike traditional batch processing systems, Fluo processes updates in real time, making it ideal for applications that require immediate insights. Built on top of Apache Cumulo, it leverages a distributed key-value store to manage data efficiently. This makes Fluo particularly powerful for use cases like real-time analytics dashboards, fraud detection, and monitoring systems. YARN, or yet another resource negotiator, is a key component of the Apache Hadoop ecosystem. It's responsible for managing and allocating resources across a cluster of machines. YARN enables multiple data processing engines like MapReduce, Spark, and Fluo to run on the same cluster without conflicts. By separating resource management from data processing, YARN provides a flexible and scalable environment for distributed computing. Integrating Apache Fluo with YARN brings several advantages. First, YARN handles resource management, ensuring that Fluo applications run efficiently across a cluster. This integration also provides scalability, allowing Fluo to process larger datasets as the cluster grows. Additionally, Fluo benefits from seamless integration with the broader Hadoop ecosystem, including tools like HDFS and Cumulo. Finally, YARN fault-tolerant architecture enhances the reliability of Fluo applications. Observers are the core building blocks of Apache Fluo applications. They are essentially functions that react to changes in the data stored in Cumulo. When a piece of data is updated, Fluo triggers the relevant observers to process that change incrementally. This allows applications to maintain real-time consistency without reprocessing entire datasets. Observers can be written in Java and are designed to run in a distributed environment, making them highly scalable. Transactions in Apache Fluo ensure that data changes are processed reliably and consistently. Fluo leverages Cumulo's support for ACID transactions, which means that all changes within a transaction are atomic, consistent, isolated, and durable. This is crucial for applications where data accuracy is paramount. Transactions also support different isolation levels, allowing developers to balance performance and consistency based on their specific requirements. Notifications in Apache Fluo are lightweight signals that trigger observers when data changes occur. Rather than constantly polling for updates, Fluo uses notifications to efficiently inform observers about relevant changes. This minimizes processing overhead and ensures that observers are only activated when necessary. Notifications are stored in Cumulo and processed by the Fluo framework, making the system both scalable and responsive. The architecture of Apache Fluo is designed for distributed, incremental processing. At its core is the observer framework, which defines how data changes are processed. Cumulo serves as the underlying storage system, providing scalable and consistent data management. YARN handles resource allocation, ensuring that observers are executed efficiently across the cluster. This combination enables Fluo to process massive datasets with low latency and high throughput. The workflow of a Fluo application on YARN begins with data ingestion into Cumulo. As data changes occur, Fluo generates notifications to trigger relevant observers. These observers are then executed across the cluster, with YARN managing resource allocation to ensure optimal performance. This workflow enables real-time processing of large datasets while maintaining consistency and fault tolerance. Setting up Apache Fluo on YARN requires a few key steps. First, you'll need a working Hadoop cluster with a Cumulo installed. Next, download and configure the Fluo distribution to work with your environment. Once configured, you can deploy your Fluo application to the cluster. YARN Web UI provides valuable insights into resource usage and application performance, helping you monitor and optimize your deployment. Writing your first observer in Apache Fluo is a great way to understand how incremental processing works. Observers extend the abstract observer class and implement the process method, where you define the business logic for handling data changes. Within this method, you can read and write data, generate notifications, and trigger other observers. Testing with sample data helps validate your logic before deploying to a cluster. Effective data modeling is crucial for optimizing performance in Apache Fluo. Data in Fluo is organized using a row, column family, and column qualifier structure, similar to a cumulo. Choosing appropriate value types and encoding methods can significantly impact storage efficiency and processing speed. Designing a schema that aligns with your application's access patterns is essential for achieving optimal performance. Optimizing performance in Apache Fluo involves several strategies. Batch mutations reduce the number of write operations, improving throughput. Observer chaining allows you to process data in stages, reducing memory usage. Tuning YARN resource allocations ensures that observers have sufficient CPU and memory. Monitoring key metrics like processing latency and resource utilization helps identify bottlenecks and optimize further. Apache Fluo provides robust fault tolerance mechanisms to ensure data consistency and application reliability. Transactions can be rolled back in case of failures, maintaining data integrity. Checkpointing allows observers to resume processing from a known state after a failure. YARN built-in failure handling capabilities further enhance the resilience of Fluo applications, ensuring that processing continues even if individual nodes fail. Monitoring and debugging are essential for maintaining healthy Fluo applications. YARN provides detailed application logs that help diagnose issues. Fluo's Metrics API exposes key performance indicators that can be integrated with monitoring tools. Observer tracing allows you to track the flow of data through your application, identifying potential bottlenecks. Performance profiling tools help optimize resource usage and processing speed. Security is a critical aspect of any distributed system. Apache Fluo integrates with Hadoop's security features, supporting authentication and authorization mechanisms like Kerberos. Data encryption ensures that sensitive information is protected both at rest and in transit. Audit logging provides visibility into data access and modifications. Secure communication protocols protect data as it moves between components. One compelling real-world use case for Apache Fluo is in financial analytics. Real-time fraud detection systems can leverage Fluo's incremental processing to identify suspicious transactions as they occur. Risk assessment models can be updated continuously as new data becomes available. Portfolio monitoring applications can track changes in asset values and trigger alerts when thresholds are crossed. Regulatory compliance systems can ensure that all transactions are logged and auditable in real time. Another powerful use case for Apache Fluo is in EOT monitoring. Processing sensor data in real time allows for immediate responses to changing conditions. Anomaly detection algorithms can identify unusual patterns that may indicate equipment failures or security breaches. Predictive maintenance systems can schedule repairs before issues occur, reducing downtime. Smart city applications can optimize traffic flow, energy usage, and public services based on real-time data. When choosing a real-time processing framework, it's important to understand how Apache Fluo compares with other technologies. Unlike Spark Streaming, which processes data in microbatches, Fluo provides true incremental processing. Compared to Flink, Fluo's strength lies in its tight integration with Accumulo for consistent state management. While Storm excels at event processing, Fluo is better suited for complex stateful computations. Traditional batch processing systems like MapReduce are less efficient for real-time use cases. Compared to traditional batch processing, Apache Fluo offers significantly lower latency by processing data incrementally as it arrives. This approach also leads to more efficient resource utilization, as only the changed data needs to be processed. Fluo's transactional model ensures strong data consistency, which is often challenging to achieve with batch systems. However, batch processing may still be more suitable for use cases where low latency is not critical and data can be processed in large chunks. Developing effective Apache Fluo applications requires following several best practices. Designing observers to be idempotent ensures that processing the same data multiple times doesn't cause issues. Keeping observer logic simple and focused improves maintainability and performance. Using batch operations for multiple writes reduces overhead. Regularly monitoring performance metrics helps identify and address issues before they impact users. When working with Apache Fluo, there are several common pitfalls to be aware of. Observer loops can occur when observers trigger each other indefinitely, leading to performance issues. Resource contention can arise when multiple observers compete for the same resources. Data skew can cause some nodes to become overloaded while others remain idle. Inefficient transactions can lead to bottlenecks and reduced throughput. Understanding these issues and implementing appropriate safeguards is key to building robust Fluo applications. Scaling Apache Fluo applications effectively requires careful planning and monitoring. Horizontal scaling involves adding more nodes to the cluster to handle increased load. Proper resource allocation ensures that each observer has sufficient CPU and memory. Load balancing distributes work evenly across the cluster to prevent bottlenecks. Performance tuning involves optimizing configurations and code to maximize throughput and minimize latency. Apache Fluo integrates seamlessly with other components in the Hadoop ecosystem. HDFS can be used for storing large datasets that are processed by Fluo. Spark can handle batch processing tasks that complement Fluo's real-time capabilities. Kafka can serve as a data ingestion layer, streaming data into Fluo applications. Zookeeper provides coordination services that help manage distributed Fluo deployments. The future of Apache Fluo looks promising, with active community development driving new features and improvements. Performance enhancements are continuously being made to increase throughput and reduce latency. Cloud integration is becoming increasingly important, with efforts to make Fluo deployments easier on platforms like AWS and Azure. As real-time processing becomes more critical across industries, new use cases for Fluo continue to emerge. The Apache Fluo community is a valuable resource for learning and troubleshooting. The official documentation provides comprehensive guides and API references. Mailing lists offer a platform for asking questions and sharing knowledge with other users. The GitHub repository contains the source code and issue tracker for reporting bugs or requesting features. Community forums provide a space for discussions and collaboration on Fluo-related topics. Before getting started with Apache Fluo, there are several prerequisites you should have in place. First, you'll need Java 8 or a higher version installed on your system. A Hadoop cluster running version 2.6 or later is essential for YARN integration. Accumulo version 1.7 or newer must be installed and configured. Finally, a basic understanding of distributed systems concepts will help you grasp Fluo's architecture and workflow more easily. Installing Apache Fluo involves several key steps. First, download the latest Fluo distribution from the official website. Next, Configure the Fluo.properties file with your cluster settings, including Accumulo and Zookeeper connection details. Set up an application directory with your observer code and dependencies. Finally, deploy your Fluo application to the YARN cluster using the provided deployment scripts. Configuring Apache Fluo properly is crucial for optimal performance. The Fluo.properties file contains essential settings like Accumulo connection parameters and Zookeeper quorum information. YARN resource allocation settings determine how much CPU and memory each observer can use. Accumulo connection parameters specify how Fluo connects to the underlying storage. Observer configuration allows you to customize behavior for specific processing needs. Testing is a critical part of developing reliable Apache Fluo applications. Unit testing allows you to verify individual observer logic in isolation. Integration testing with Mini Fluo provides a lightweight environment that simulates a full cluster. Performance testing helps identify bottlenecks and optimize resource usage. Validating business logic ensures that your application produces correct results under various conditions. Deploying Apache Fluo applications can be done through various strategies depending on your environment and requirements. Manual deployment is straightforward for development and small-scale production use. Automated CI/CD pipelines provide consistent and repeatable deployments for larger applications. Rolling updates allow you to update applications with minimal downtime. Blue-green deployments enable zero downtime releases by switching between two identical production environments. When working with Apache Fluo, you may encounter several common issues that require troubleshooting. Connection failures to Accumulo or Zookeeper can prevent applications from starting. Performance bottlenecks may occur due to inefficient observers or resource constraints. Observer errors can result from incorrect logic or data handling. Resource exhaustion happens when applications consume more CPU or memory than allocated. Understanding how to diagnose and resolve these issues is key to maintaining stable Fluo deployments. Optimizing the performance of Apache Fluo applications involves several key areas. Observer batching allows you to process multiple notifications together, reducing overhead. Transaction optimization involves minimizing the scope of transactions to improve concurrency. Properly sizing YARN containers ensures that observers have adequate resources without wasting cluster capacity. Tuning garbage collection settings can reduce pause times and improve overall throughput. Implementing security best practices is essential for protecting Apache Fluo applications. Enabling authentication ensures that only authorized users can access the system. Using encryption protects data both at rest and in transit. Implementing authorization controls what actions users can perform. Regular security audits help identify and address potential vulnerabilities before they can be exploited. Effective monitoring and alerting are crucial for maintaining healthy Apache Fluo applications. Integrating with YARN metrics provides insights into resource usage and application performance. Custom metric collection allows you to track application-specific indicators. Setting appropriate alert thresholds ensures that issues are detected before they impact users. Creating comprehensive dashboards helps visualize key metrics and trends over time. In summary, Apache Fluo provides a powerful platform for real-time incremental processing of large datasets. When combined with YARN, it offers scalable resource management that enables efficient distributed computation. Observers serve as the core processing units, reacting to data changes with custom business logic. The integration with the broader Hadoop ecosystem makes Fluo a versatile tool for modern data processing needs. Understanding these key concepts is essential for leveraging Fluo's full potential. Thank you for watching this comprehensive tutorial on Apache Fluo YARN. We've covered everything from core concepts to real-world use cases, giving you a solid foundation for working with this powerful technology. If you found this video helpful, please like and subscribe for more tutorials on big data technologies. Don't hesitate to leave a comment with any questions or topics you'd like us to cover in future videos. Be sure to explore our related tutorials and consider joining the Apache Fluo community to continue your learning journey. And that wraps up our explanation. If you found this useful, please hit the like button and share it with a fellow developer. Don't forget to subscribe for more technical tutorials. Thanks for watching, and I'll see you in the next one.